So in this session we will study about elements of greedy strategy and activity selection problem. In the previous session you may have already seen another algorithms. Now this is another different strategy that we will going to be exploring, and with that we are also going to explore other problems that lie in this domain. So we'll try to discuss more and more greedy techniques that uses specifically these kinds of greedy strategy and greedy algorithms. So starting with that, greedy algorithms are just a typically optimization algorithm. So what they happen is that you have been given a problem, and on that problem you have to establish a goal. The goal can be that you have to maximize or minimize, something like you have to maximize or minimize profit based on a specific number of constraint. For example, like that you have given a bag and you have to put a number of mangoes in this bag. So you have to maximize the number of the constraint that is given to you. They have to maximize the number of mangoes that you can put in the bag. So the capacity of the bag will be given to you. So you have to apply greedy strategy or greedy algorithm in order to maximize the number of mangoes in the bag. So in these particular kinds of problem we need greedy strategy, because at that particular time, because we are given a number of constraints that the bag capacity is this, and constraint and the goal is that you have to maximize the number of mangoes. So you can easily understand like it that when you are dealing with greedy problems, you have to be given a problem with a number of constraint and a goal. So these three basic things that you will be given. So if we are talk about the optimization problem itself, if we just formalize this particular method, so what will happen here is that an optimization problem, so if in general we talk about optimization problems, an optimization problem has n inputs, meaning that you will be given a input set or a candidate set, or this can also be called as a domain. So what do I mean by this is that you will be presented with the number of inputs. So in our example, the number of inputs was your mangoes. We are required to make, or we are required to obtain a subset of this domain. So you will be presented with the optimization problem that has n inputs, and from this n inputs you have to make a subset of this n inputs, which will be called a solution set. And keep that in mind that this particular subset, this is the subset we have to create. This will be created from the candidate set, or we are calling it as C. So so if I am calling this as the input set as a C, that is referred to as input set or a candidate set or a domain, and then we are required to obtain a subset of this set C. So I'm calling this subset as a solution set. Now I'm calling this as S. So what do I mean by this is that this is the goal. So you will be presented with the number of input. From that inputs, you have to create another solution. So that solution will be a subset of the inputs, meaning suppose if you are given an input set with the calling it as a variable C, and then you have to require to make another set calling it a variable S. The name of the set is S, and that set have to be a subset of the input set. So S should be a subset of C. So simplifies that. And how will you add the inputs into a subset, that is a solution set? So that will be based on the number of constraints or condition that will be given to you in a problem. Like the example that I've started with, that you have given the number of mangoes, that you have to put the mangoes in the bag, and that bag has a constraint. That bag can have this much liter of capacity, like 4 liter of capacity, 5 liter of capacity. After that you cannot input more mangoes. So this will be a set of constraint. So other thing is goal is that you have to create a solution set where the input is a bigger set, and the solution set is the maximum number of mangoes that you can put into the a basket with a capacity of 5 liter. So if you want to understand this problem, it's very easily understandable like this. Now any subset like we have created a subset which represent the solution of the input of the optimization problem. Any subset which satisfies the given constraint. So suppose you have satisfying the given constraint and you have put enough mangoes in the basket, and that particular solution set will be referred to as a feasible solution. Feasible means that it can be an optimal solution, it cannot be optimal solution, but it will be a solution. So what do I mean by this is that if you are putting 100 mangoes in a basket by using the given set of a constraint, that is a solution. So suppose you have given 200 mangoes and you are given this task to put the mangoes having a 5 liter capacity bag, and you have to maximize the number of mangoes. So suppose you are putting 90 mangoes in that bag and you are following the constraint that the capacity of the bag is only 5 liters, so you cannot put more mangoes than that. So in that particular example, if you consider that if you are putting heavier mangoes that are larger in size, the number of mangoes become less. But if you are following the constraint, suppose you are able to put 90 mangoes in the basket. So this is a feasible solution. It is not the optimal one. This is the feasible solution. So what do I mean by this? In that, if you are only putting smaller mangoes, you will be able to get 120 mangoes in that basket, same basket in which you are getting 90 mangoes earlier. So what do I mean by this? 120 will become the optimal solution and 90 is your feasible solution. Anything that ranges from a 90 to 100 or 110, that is not close to the best solution, that will be referred to as a feasible solution. So anything which just satisfies the constraint of the algorithm can be a solution, and you are able to build a solution set. So can be a solution, but that solution is a feasible solution, not the optimal solution. Keep that in mind. So we need to find a feasible solution that either maximizes, minimizes the given objective function. So in our example, our objective function was to maximize the number of mangoes. The feasible solution that does, so there can be number of feasible solution, like you can put 10 mangoes, you can put 20, you can put 100, 120, and the solution which is maximizing the number of mangoes will be your optimal solution. So these are the four main things that you have to keep in mind. The first is the input set, and input set is also referred to as a candidate set. Then you have to make a subset of this input set, that will be referred to as a solution set. And another thing is that you have to satisfy the number of constraint. Another thing is that you can obtain any number of feasible solution, but optimal solution will only be one. So we have done this till now. Now the procedure, the step-by-step procedure, if you understand, of any greedy strategy will be very simple. So first of all, again the similar thing that we have already discussed, that you have to take one input at a time. Suppose you are given 10 inputs. First take one input out of these 10 inputs. At this stage, now you make a decision that this particular input satisfies all the constraint and it can be part of your solution set. So our selection input X is guided by some selection function. So we are calling that selection function as select. So keep that in mind. One more variable we are adding here is select. Now check if the inclusion of X gives the optimal solution. So there may be many feasible solutions, but there will be only one optimal solution. So if the inclusion of X, suppose I have from out of 10 samples, I have taken one sample and that sample is called as X. And if by including X, I am coming close to the optimal solution, then I will add that X into the solution set. So that particular solution set obviously will not be complete. So we are calling this, at this particular stage, we are calling this solution set as a partial solution set. Now, on the other hand, if the inclusion of the input x results in an infeasible solution, so that x will not be included. Suppose again from the same example, if you take if you have very little capacity of a basket, like it can only store like 1 or 2 mangoes. Now by including one mango that is very heavier, that is like 2 or 3 kgs, like it's very heavy, the one mango is very heavy, it's 2 or 3 kgs is very heavy, but being very big mango, if you include it in a basket, it will exceeds the capacity of the basket. Now you will not include this particular mango in the basket because it is resulting in a infeasible solution, because it is exceeding the given capacity. Similarly, if you have taken a smaller mango that have a very small capacity, you can easily include that smaller mango in a basket. So if the input, in this case a bigger mango, if it exceeds the capacity of the basket, then you cannot add this because it leads to a infeasible solution. But if on the other hand the mango is very small, it means that you can add it to the basket because it is again leading towards the feasible solution. Okay, so this is it. So little bit, if I talk about that, there are what we have discussed till now, that first we have to include an element, the input, from the input, saying this element as x from the domain C. So I'll just why I'm explaining and again, because I will now be introducing some mathematical factors here. So that is why again I'm discussing more and more, and then we'll talk about the mathematics of this. Now first thing is that you have taken an input from the input domain or a candidate set C. So calling this input as x. Now the second step is that you have to check whether it's a feasible solution or not. Now if the solution is feasible, it means it can be added to the solution set. So if it is there, then you can simply take the solution set and do the union with x. Now initially the solution set will be empty, and then when you do the union of x with it, now the solution set contain only x till now. But if that x is leading towards a infeasible solution, then you can directly discard it and your set will remain empty, your solution set will remain empty. Now third step is you have to repeat this process again and again until and unless until you will get either it maximizes the case, or what is the objective function, depending upon that, either it maximizes or minimizes, whatever the case may be, until and unless you get you are able to get when the capacity is full and you are able to get it, so you can stop it right there. So what you will obtain in the end will be called as a optimal solution. So you have to continue until the solution set S is filled up, or C, that the candidate set is fully exhausted. So whichever is this earlier, you keep doing the process again and again, whatever is it, then in the end you will get the optimal solution. So what do how do I formalize this, that the greedy technique formalization? So again a candidate set from which a given solution is created, it may be nodes, edges in a graph, etc. So we are calling this set as a set of given values or a set of given candidates. So firstly take out the candidates from the set, and then one by one take the candidate set, examine it, and then put it into the solution set. So the next step is, if we formalize it, the next step would be a solution set S, which the solution set S, keep that in mind, the solution set S is a subset of set C. Now, in which we build up the solution. So, this structure contains those candidate values which are considered and chosen by greedy technique to reach a solution. So, again take the input x, apply that this particular set can be included in a solution set. If it satisfies those conditions, then you can easily include this into a partial set that can lead to an optimal solution. So, second step is set of selected candidates which is used to give a selected optimal solution. Now, third step, a function. So, we are calling this as function because why I am doing this steps, because these particular variables like solution, select, feasible, we will be using this in an algorithm. So, a function says solution to test whether a given set of candidates give a solution. We are not at this point, we are not testing that the solution is optimal or not. So, we are only just testing that if we are able to get a solution that it does not violates any condition, then we will be able to add this particular function. So, with the use of the solution function is that you can simply check that a particular element can be added in the solution set or not. So, another is a selection function. So, we are calling this selection function as select. Now, this select function will choose the best candidate C to be added to the solution set. So, another thing is that another variable that we will be introducing is a function say feasible. Now, feasible function will be to test that if a solution S can be extended to a solution. So, again the feasible solution will only test that this particular inclusion of a input can be leading to a feasible solution. Another thing is the number of constraints. So, like if you want to maximize or minimize, so this will be called as an objective function. Like in our example of mangoes, we want to maximize the number of mangoes in a basket. So, our objective function was maximizing. So, another thing is objective function is another variable. So, we have seen another solution function, select function, feasible function and objective function. These are the four variables that we will be using in greedy technique. Now, if you take a look at the example here, so example will be that you will be given a multi-set. So, if you check the example here, multi-set, this is not a set because this is particularly a set, the example that is given here, but the solution will be given in a multi-set. So, what is the difference between a set and a multi-set is that in a set you cannot repeat the values. So, suppose 1, 2, 3, 4, this is a set. 1, 1, 2, 3 is not a set because 1 is repeated 2 times, but 1, 1, 2, 3 is a multi-set. Okay. So, keep that in mind. In this example, the question is given in a set, but the solution is in multi-set. So, check here, you are given the number of denominations of rupee notes like from 1 to 5, 10, 50, 100, 500 and 1000. So, this is your candidate set. So, I am taking it as example, same example like that we have considered like the mango example. Now, it is very similar to that. Now, firstly we have taken the candidate set which contains the number of denominations in rupees. Now, the goal here is to collect the amount of 283. Okay. So, the goal here is to get the main goal is to get 283 rupees from this candidate set. Now, the constraint are that the notes, the number of denominations should be minimum. So, you have to make the node set in such a way that you will get minimum nodes to create rupees 283. Okay. So, if we allow a multi-set rather than a set in that sense, so you can add more number of same number of nodes together. So, suppose start with the maximum possible result. So, take the input x. So, I am taking 1000 input. Okay. So, suppose I am taking a 1000 rupees note. Is that note can be considered? No, because it violates the condition that that your goal is 283 rupees and 283 is less than 1000. So you cannot add a 1000 rupees note. So you go to the next note, that is the next minimum note, that is your 500. So is 500 is again greater than 283. So it means 500 cannot be added into the solution set as. So you can also discard this. Can 100 be added into the solution set? 100 is less than 283, so it can be added. Okay. So firstly I have added 100. So now this particular problem, this particular solution set is now filled with only one denomination, that is 100. Now can another 100 be included? Yes, another 100 can also be included, because the addition of these 200 leads to 200 rupees, which is again less than 283. So can I add another 100? No, because if you add another 100, it will becomes greater than 283. Again, we are not reaching to our goal. Okay, so it is not leading to a feasible solution, so we are discarding it. So another is that you can add 50 rupees. Yes, again 250 is less than 283, you can add it. Now another is, can you add another 50? No, you cannot add it, because it leads to 300 again, which is greater than 283. So can you add it 20? Yes, you can definitely add 20, because it leads to 270, which is again less than 283. So in the similar way, you can add 10, 2 and 1. So if you see here the solution set that you are getting, you are taking the candidate set values, examining it. If it is leading to a goal state, only then you are adding it to the solution set, otherwise you are neglecting it. Okay. So first, this is the example that where if you check here, the function solution checks whether a solution is reached or not. Okay. So however, this function does not check for optimality, so it will not check for optimality. So in case minimum number of problem, the function solution finds the sum of all values in the multiset. So if you say fixed amount here is 283, if any stage it leads to more than 283, the solution function will say that it is not feasible. So it will discard it and it will go towards another variation possible. Now another function that we use is select. Now select function will find the best candidate value, that is input from that we are getting the input from the candidate set. Okay. So how this function behaves is that first you take the input x. By adding this x, if you are getting closer to the solution, then it will add it. But if it is not leading to a solution, then you can simply discard it. So the similar way that if we select a 1000 rupees note, 500 rupees note, it will be directly discarded by the select function, because it is leading to a infeasible solution, because it is becoming greater than 283. Okay. So now with this, another function that we are talking about is feasible function. So the feasibility is that you just when you are selecting a particular function, you check the feasibility of that function. So these are very interrelated function. So when you take the select function, it will select the variable. So it will select the input from the candidate set. Now you check that this input can lead to a feasible solution. Suppose you are taking 100. 100 is again less than 283, so it means it is leading to the feasible solution. So you will take the input of 100 and include it in the solution set. So this is how this works. Another thing is that you have to take care of the objective function. Now objective function here is that you have to the objective function is that you have to get the minimum number of nodes. So this objective function can return that the number of nodes that you are getting in the end are minimum. Okay. So for this, for example, in this you are getting 7 nodes, and if you try any other possible solution, you will not get it. So how is this working? Because you have started from the increasing order. So from the increasing order, you go from 1000 to 500 to 200 to 100. So from that particular range, you are able to get it. So this is way that you are following a certain procedure, then you will be able to end with the optimal solution. So this objective function ensures that you are following the objective that what is given in the problem. If you check the algorithm of a greedy technique, it's very simple. The input here is the input domain, that is the candidate set, and the candidate set of size n. So you will input, suppose if there are 5 number of elements included in the set, so you will input the 5 elements, along with that you will enter 5 also. So 5 will the size of the set. And another is that you have to just start the function select solution feasible. So these are 3 functions that will only return boolean variable, either true or false. Another is that the candidate function will return the element, or the element that is being input. Now if you check here, you will in the end get a solution set, and the solution set will contain again the subset. The solution set will be the subset of a candidate set. So you will start the S solution set with a 5, because it does initially it does not contain anything. Now you have to take a loop until your solution is becoming true, or that candidate set becomes empty. Okay. So now firstly you will take up the element and you run the function select. Now x will be the input element. Now you are taking one element and you are applying a select function of it. So it will perform the procedure that this particular thing can be selected, because if it is leading to a feasible solution, only then it can be selected. So you will select it, and when you take up that element will be deleted from the candidate set. Now when it is deleted, so you will check the feasibility of this particular x. If it is feasible, so now you run the feasible function. If it is feasible, then you will take the union of that particular input with the solution set and you will add it in the S. If it is not, then you will say, now this is not I want to add in my solution set, and you will discard it, and then you will move on to the another candidate. So this will go on till your candidate set is empty. This particular procedure will be again repeated again and again. In the end you will get a solution set. So this is the basic procedure of a greedy function. Now with this we'll again discuss about activity selection problem, that also comes under greedy technique. So activity selection problem is a classic optimization problem that occurs. Now here what we have to do is that it involves selecting a maximum number of non-overlapping activities from a set of activities that require exclusive use of shared resources. So I will discuss it. Now check, the example here is given like that you are given 10 activities and like A1 to A10, and your start time is 1, 2, 3, 4, and the finish time of each activity is given in the function. The solution is very simple. Firstly, you arrange the activities in increasing order of their end time. Okay. So what do we mean by this? Like increasing order of their end time. So if suppose activity A1 is finishing at 3, okay, so the smallest thing you are getting here is 3. So you add, so you write A1 first. Another is 4. Okay. So finishing time is 4. Now it corresponds to the activity A3. So write that activity here. Okay. So it means A3 will be added, and then another finish time is 5, which belongs to A2. In the similar way 7, 9, 10. So arrange all the activities in the increasing order of their end times. After adding it, what you simply draw a graph. Okay. So suppose A1 is starting from 1 to 3. So you draw a line from 1 to 3. Okay. Similarly, A3 is starting from 3 ending at 4. So it is again a non-overlapping, because activity A1 is finishing at 3. From 3, A3 is starting. So this is not overlapping. So there is no problem with it. Another is A2. So A2 is a 2 to 5, which is a overlapping activity, as you can see on the graph solution as well. So discard this particular activity. So we do not need the overlapping activities. Okay. So move on forward with A4. A4 is starting from 4, ending at 7. So starting at 4, ending at 7. Again, it is not overlapping with anything. So it's good to go. Another thing is 8 to 9, A6, 8 to 9. A6, 8 to 9 is again not overlapping. So you can simply write it. Another thing is that A6 activity is moving from 8 to 9, so no problem there. And then there is activity that is A5. So A5 is starting at 7, ending at 10. So starting at 7, ending at 10, this is the overlapping activities. You can simply discard this activity and then you move forward with A7, which is again 9 to 11. So you have to draw it A7, 9 to 11. So if you discard A5, this is not overlapping. So you just write A7. Similarly for A9, it is again not overlapping, 11 to 12. A8, which is overlapping from 9 to 13. So you simply discard that A8 activity, and then there is another activity from 12 to 13. So when you draw it, you will get to realize that which of the following activities are overlapping, and by deleting those activities, you will be able to get the non-overlapping list of activities. So this is simply the solution. So what we are doing is that we are taking the input from the candidate set, adding it to the solution set, checking the feasibility. Now in our example, in activity selection problem, A2, A5 and A8 is not leading to a feasible solution, so we will discard this. So in the end, the solution will be A1, A3, A4, A6, A7, A8, A6, A7, A9 and A10. So this will be the solution for your activity selection problem. So this is how you get out of it. So first of all, always draw the graph, and first step is to arrange in the increasing order of their end time, and then draw the graph, you will get it. Okay. So this is it for this session. So in this session, we have studied about the greedy, introduction to greedy algorithms, and we have seen one algorithm, that is we have seen the journal algorithm of greedy's approach, and we have also seen activity selection problem. Thank you.